All right, today this is actually video 6.3. I know it says 6. Sorry, this is video 6.4, applications of rational expressions. And this is the key to 6.3. So just email me if you do have any questions. The key is in Canvas also, so you can see how you did last class. And then this document that I'm going to be using is also in Canvas if you'd like to print that off and follow along. So today we are applying all of our knowledge about adding, subtracting, simplifying radicals. And the first thing that you're going to need to remember is how to find area. So remember a square, square and rectangle are the same thing, but the thing about a square is their sides are the same. So we can just say the side length squared, so one side times the other. That's not a very good square, but pretend all the sides are the same. So that would be measure S, S, S. So area would just be this side times this side, and then it'd fill that in as we multiplied. Rectangle is we're going to call it length times width. Triangle then, remember it's half of a square, or half of a rectangle, so it'll be 1/2 length times width. And a circle is pi r squared. And you don't need to have all those memorized. The one that is on your test is rectangle or square. Maybe both, I can't actually fully remember, but those are the ones that you will need to know. Volume, you will also need to know. For any square or box, volume is length times width times height. And cylinder, you don't need to know for the test, but you do need to know for this paper. It's pi r squared times height. So remember, volume is how much we can hold in to like I guess a 3D object is the best way of saying it. So the cylinder, we find the area, so notice pi r squared is very similar, right? You find the area of that circle, and then height just imagines that those circles are stacking on top of each other. So that's why we multiply by height. Just to explain that formula a little bit more. And when it asks for a ratio, that's a comparison. So let's say that I had, if you've ever filled a two-stroke engine, like if you have a motorcycle or a lawnmower or an edger that requires a mix of oil and gasoline, they're going to have a ratio, usually I think it's like 1 to 36, so 1 part oil to 36 parts of gasoline. So that's an example of a ratio. Maybe I have 6 lemons for every 8 oranges. When I'm picking, so my parents live in Arizona and they don't have as many lemons, so maybe they have a ratio of 6 lemon trees to 8 orange trees. So a ratio is that comparison. Sometimes it's part over whole. That's more getting into a proportion, but we'll stop there with that. All right, so we are applying our knowledge, and most people call these story problems, right? And they're a little bit tricky because there's so many things working together, and it's hard to know what information is actually important and all that. So as we go through these examples, these are specific ones to what we're learning. If you do have any questions, please email me. Try to draw as many pictures as you can, and just try your hardest, right? So what is the ratio of the area of the shaded triangle to the area of the rectangle? So we'll do a ratio, right? So start there and just interpret that. The ratio of the area of the shaded triangle. So we want the area of triangle, the ratio, a comparison, to the area of the rectangle. To the area of the rectangle. So that's our goal, right? If we read that first sentence, that's what we're trying to do. Write your answer in simplified form. Yeah. The triangle's base is the same as its height. So we know that from here to here is the same as here to here. Okay. And the length of the rectangle is 8 more than the base of the triangle. So we know that from here to here is 8. All right, so now we want to find the area. So if you remember area of a triangle, we're going to have 1/2 base times height, and area of a rectangle, we're going to have length, I'm going to put width here, length, x plus 8 would be that length, right, times the height, which is x, or width, however you want to look at it, but since it is measuring height, I'll say it like that. All right, so we have 1/2 x squared over x times x plus 8. Okay, so I'm going to simplify this. So one thing that we can do, if we notice, is 1/2 times x squared. When we multiply straight across, so 1 times x squared is x squared, 2 times 1 is 2, and then it's divided by x times x plus 8 over 1. So instead of trying to divide that fraction, I can multiply by the reciprocal, if you remember. So I'll create that there. And then as hopefully you notice, we have 2 x's here, as written before. So that x will cancel out with this x, and we're left with 1 times x in the numerator, and then 2 times x plus 8 in the denominator. And that would be an expression of that ratio. So as you kind of notice what I did, I first established the target, right? So what I wanted to do, and then I broke it up into pieces. I know I did it pretty quick, but I mean, that's exactly what we're doing. All right, Steve is building a wooden box to put stuff in. The length is 12 inches more than the width. So he has this box. The length of the box is 12 inches more than the width. And we don't know the height of this box. So I'm trying to draw a little 3D there, right? So this we don't know. We do know that bottom width. We know this length. We don't know the height. Okay. We do know the volume. So we know that x cubed plus 14x squared plus 24x will equal length times width times height. And I know there's a question mark, but I'm going to put an h. What is the simplified expression for the height of the box? So our job is to get h alone. So they're multiplying, so we will divide both sides. Boom, boom. I'm going to rewrite it because I like having the monomial before. Now, I'm going to have to factor that top part, so I'm going to do that as I go. So h equals x times x squared plus 14x plus 24 all over x times x plus 2. Keep factoring. I'm going to notice that 24, well, the a is 1, so 24 is the only number I'm really working with, and I need to make sure that 24 adds to give me 14. So I have 1 times 24, 2 times 12, and there we have it, right? So I'm going to have x times x plus 2 times x plus 12. Remember, this trick only works when your a is 1. If not, we're going to have to do a little bit more advanced method. Okay. That's supposed to be a 12. I'm so sorry. If you were confused this whole time, right, x plus 12, I just forgot that one there, but it would have caused big problems at the end. All right. Okay. Whoa, start over, right? X plus 12. So I had x plus 12 there, all these places, right? So it's supposed to be x plus 12. Sorry, guys. Okay, cross off, because they're all held together by multiplication. So the height is actually 2 more than the width. Okay, so what I want you to do is try 6. If you're stuck on it, just shoot me an email and I'll send you an example of that. So go ahead and give 6 a try. And now we're going to take a look at some more, obviously. So I want you to try 7, 8, 9, and 10. Pause this, try those. I'm serious, try them. Pause this, try them. All right, so number 7, we have, I mean, there's lots of ways to think about this, but most people do 80 divided by 18, and they get 4.44 gallons. So I just want you to kind of think of that relationship. There's lots of ways to think about it. If you're still stuck on that one, like I said, just send me an email. So if I can finish a job in 5 hours, how much of the job do I get done per hour? So one job in 5 hours, if I'm consistent, that means I get 1/5 of the job done each hour, because it has to add up to the whole job being done in 5, right? So each part will be represented by 1, so 1/5. All right, if I travel 375 miles in 5 hours, what is my rate in miles per hour? So I want to know the rate, and that's going to be miles, which is a distance, per hour, which is a time, right? So I'll divide those out, and I'll get 75 miles per hour. So 10, what is the relationship between distance, rate, and time? So you've probably heard this before. Distance equals rate times time. We haven't looked at that yet. So 9 has nothing to do with finding a distance, right? We already had our distance. When we did that, we did our rate equals distance divided by time. And if we look back, yeah, if we did hear that before, distance equals rate times time, we could just divide by our t. But I mean, 9, you hopefully figure that on your own. There it is right there. And the last one I want to talk about is, what if we solve for t? So time would be distance divided by the rate. All right, so we are going to look at, so I'm jumping around because I want you to practice these problems, but I also want to give you kind of an idea, obviously, of what you're doing. So read through 12. All right, so we want to find the total gas used, right, in gallons. We'll measure it in gallons. And so that means that we need to find out how much you used on the way there plus on the way back. So, kind of think about that, right? So we have a rate that he uses gallons. We have a distance, and we're going to have a time. So that's how we're kind of looking at this, as a distance, a rate, and a time. So semi-truck gets 25% better gas mileage when it holds no cargo than when it is fully loaded. Let M be the number of miles per gallon. So we do have a rate here, right? So M is our rate, but it's when it's fully loaded. All right? So he's going to drive 80 miles. So this is kind of going back up to 7. Think of how you figured that out. Okay, and we talked about we did 80 divided by that rate. So he's going 80 miles. We're going to divide it by his rate of using it. Then it says the truck drops off the load and returns home empty. And we know that he is 25% better when it is empty. Okay. So when it's fully loaded, he's going to take longer. Okay. So this is when he's empty, right? M was when he's loaded, right? M be the number of miles per gallon when it is fully loaded. When it's fully loaded, we know that he's going to be, it's going to get better, okay? So his mile per gallon is going to get better. So on the way back, he still has to travel the same distance. Now I want you to think, 25%, if we change that to a decimal, 0.25. So he's going to get 100% of what he got when it was fully loaded, that rate, and 25% more. So that's why I have that 1.25. If you're not familiar with percentages, again, just email me, we can talk about it. Okay, so I'm going to now, so just reread 12 again, make sure this makes sense. So we have our distance divided by our rate, and it will give us the total amount of gallons that we do use. I know it's not a time, but it's very similar in the setup because it is a rate and a distance, and it'll cancel out. So if he travels miles divided by miles per gallon, if we take that fraction m, or multiply it by the reciprocal, miles will cancel out and we'll be left with gallons. So that's what we're doing right there. So here we have our miles, here we have our miles per gallon. Okay, and remember, that's when it's fully loaded. So right there, that's going to represent that. Plus, he has to return home, he's going to use gas, he's still traveling those 80 miles, but he's going to get 25% better. Now, if we multiply something by 0.25, like try it out, do something in your calculator by 0.25, it's going to get smaller. We need it to get better, so we need to keep the 100% of that gas mileage rate, but make it 25% better. There we go. Okay, so we need common denominators, so I'm going to multiply this by 1.25, this by 1.25, and I'll add, I'll multiply those first in my calculator, and then I'll add them together, and then I'll divide it by 1.25, which stayed as the denominator. And in the end, after I do all that calculator work, we have a way for him to figure it out for every trip that he goes on. He can just do 144 divided by that rate for this trip. All right, so try 13. It's very similar. And then I'll post the key as well. Okay, so 14, actually, yeah, let's do 14. So a bicyclist rides 5 miles out and then rides back. His speed returning is reduced 20% because he goes uphill. Let R be his speed in miles per hour riding out. What is the expression that represents his total time riding out and back? So we're going to have the time that it takes him to ride out plus the time that it takes him to ride back. So remember, time is distance divided by the rate. So we know he's going 5 miles out, 5 miles back. Now we need to account for his rate. His speed returning is reduced by 20%. Let R be the speed in miles per hour riding out. So 5 divided by his rate, right here, riding out. And then when he returns, he's going to go uphill. And it's reduced by 20%. So if we think normally he has 100% of that rate, if we take away from 100% of that rate 20%, we're going to get 0.8, changing it to a decimal. So he's going to get 80% of what he can normally do if it's reduced 20%. Okay, now I haven't actually put this in a calculator and I don't have one nearby. I already did this one in the calculator earlier. So I am going to multiply so that we have a common denominator, and then I'm going to do 5 times 0.8 plus 5, and then I'll put that in my calculator, divide by 0.8, and I'll get my answer, but I'll let you do that. So take a look at the homework, take a look at the problems that I didn't do. I will post a key, and if you have any questions, let me know.